Now, ideally, if you understood everything that we've done so far, you understand every bit of what I'm going to talk about here. It's going to go fast, so if you don't understand, you're probably going to get lost pretty quick and you need to look back at the video. Okay, either the quick video I'm going to do now or the longer ones from the MCR class. So we got the y equals t squared function. As a graph, just for reference, we don't really need the graph to answer the questions, okay? These questions are on the document for today, which I don't have enough of and didn't distribute, but it'll be on the website. So, first thing you're asked to do is vertically stretch this function by factor of 0.015. I don't mean graph the vertical stretch, because that's a small factor. It'd be hard to graph that. Everything would shrink down real close to the x-axis. Everything would look almost flat, right? Okay, we're not going to actually do that, but we vertically stretch by factor 0.015, and what you're asked for is, what's your function going to be? Okay, well, what do you do when you vertically stretch? Well, vertical stretch by factor 0.015 moves everything 0.015 times as far from the x-axis, right? Means all your y values are multiplied by 0.015, which means that you're going to multiply your y values by 0.015, and you're going to get y equals 0.015 times t squared. Okay? Then you shift negative 20 units vertically. Everybody understood that pretty quickly. Just subtract 20 from that, and you get 0.015 t squared minus 20. And then you horizontally shift 80 units. Now, people didn't do well with horizontal vertical shifts and stretches on the test. Some people did. Most people didn't know the difference between a vertical stretch and a vertical shift. Okay? Demonstrated that adequately on the test. Okay? So somehow y'all are missing this. You're going to need to review this. Okay, anyhow, horizontal shift of 80 units. How do you do a horizontal shift? People didn't do well with horizontal shift either, but this is the confusing one. Okay? You replace t with t minus whatever your horizontal shift is. So you replace t with t minus 80. And you get, well, you replace t with t minus 80, and your t squared is going to become t minus 80 squared, right? That's the rule. We went over a lot with graphs, how you do exercises, all kinds of things to show you why this is, because if you know why it is, you're more likely to get it right on a test, especially if you haven't reviewed. I mean, I'm sure everybody reviewed, because as I say, results in the test were not much better. They're much better than what I usually get on a midterm test in the pre-calculus class, okay? Even though some of you were a lot lower than I expected you to be, and I think you're going to be able to pull that up, the results for the class as a whole were not bad, okay? I mean, we want them to be better, okay? But I'm not displeased with the class's performance as a whole, okay? Trying to find ways to make it even better. Okay, well, one way to make it better is kind of review some of these things, okay? A little better than you did. And you know, it's a math course. It's hard to know exactly what to do. I'm just saying, yeah, review better. Okay, well, anyhow, so this is going to be the form of the function. Then the question is, I'm going to call this function g of t. So here's your g of t function, right? Is that quadratic? Well, there's kind of evidence that it might be, because if you think about it, when you vertically stretch a point at the origin, you don't move it because it's zero distance from the origin, and no matter how many times you stretch that to get it further or closer to the origin, it never goes away from the origin, right? So when you multiply 0 by any number, you get 0, so 0, 0 is going to stay at y equals 0, right? When you vertically stretch it, it's still going to be at the origin. Then when you horizontally and vertically shift it, well, you vertically shift it negative 20 units, that's going to take it 20 units down. Horizontally shift it 80 units, it's going to be at 80 negative 20, right? And for this factor, you've flattened out the parabola a lot, but its vertex is going to go to that 80 negative 20, right? It's still going to be a parabola, and we haven't proved it, so you can't really use the idea to prove anything, but that's a pretty good indication it's quadratic, because any parabola that opens vertically with a vertical axis of symmetry represents a quadratic function and vice versa. If it's a quadratic function, it'll be represented by such a parabola, okay? So you identify parabolas with quadratic functions. Well, there's an indication, but the real definition, and people in MCR class came up with it, is that it's quadratic if it's of the form y equals at squared plus bt plus c. That's what it means to be quadratic. Now, is all this stuff that you should know from what we've done? Yeah. So we're not doing anything new, but we're putting it into a bigger context, okay? Another thing is, this could easily be a model for a flow situation, for the model, okay? And the numbers are actually even realistic from the bottom. Okay, well, it is quadratic if it can be put into this form. Now, just like a function is linear, if it can be put in the form y equals mx plus b, right? Okay? So, what we want to do is see if we can put this in the form at squared plus bt plus c. Well, what do you do to put this in a different form? Well, you expand it. Okay? You expand and simplify this expression here and see if it ends up being an at squared plus bt plus c. So first thing you got to do is you got to simplify what's in parentheses, but there's no simplification to t minus 80. That doesn't simplify in any way. Then you exponentiate order of operations. You square this. How do you square this? You multiply it by itself using not superstition, because superstition will tell you it's t squared minus 80 squared. Okay, that's not what it is. That's not consistent with the distributive law. Use the distributive law, multiply that, and here's what you get. And people are real good at doing details of distributive law, okay? One of the first things we did, you actually seem to have remembered that, seem to have done it on the test, okay? There's some other things maybe you didn't remember as well as you should, but they'll come back. And they're actually, a lot of them are just easier with distributive law, just details that you might have lost track of. Okay, anyhow. So you do the distributive law, and I'm not going to do that. I've done that many times, and you've done it many times, and you're good at it. So there it is, right? Distributive law proves that this squared is this. Then you use the distributive law and multiply through by the 0.015, and then you subtract your 20. And when you do, you get this.
Yeah.
Okay? So I've got to pull that down and put it up here. So we get this. And that is in the form at squared plus bt plus c, and this is quadratic. Check mark, checked it, it's quadratic of this form, right? Now, this is important because this sets the stage for what we're doing right now, which is going to be, this week, quadratic functions and complex numbers. Complex numbers, everybody finds easy. Quadratic functions brings together everything we've been doing in a way that clarifies what we've been doing and also gives you the skill to work with quadratic functions.